This video is on the fourth of the big questions, whether there is measurement error. And once again, we can call upon a great quote from Yogi Berra. I usually take a 2-hour nap from 1 to 4. Okay, so measurement error occurs when the key explanatory variable has error. We'll talk in a bit about the control variables. Okay, what causes measurement error? Well, there are 5 main causes. One, there's bad coding, or the old fat finger effect. Second, there could be lying. There's a lot of surveys where people are answering questions about their income, whether they're employed, their drug use, many other things that may be sensitive topics, and so people might lie about these things. Poor recollection on things. So something like a diet study, or even a question about how much marijuana did you use in the past year. If it's just a couple times, it may be easy to remember. If it's many times, maybe 15 to 30 times, you're probably not going to remember exactly how much. And so there's going to be error in the such variables when you're trying to remember things. If there's an aggregated variable, something like gross domestic product or something like the unemployment rate, those are going to be measured there just because they're taking a sample. They're based on samples, not always the full extent of activity or the full extent of the population. And then there's this one that I kind of learned late in my career, that there could be accurate data. Everything's good. There's no lying, there's no bad coding, but it's just poorly representing the key concept that you're trying to measure. Okay, and this applies to the hot hand, as we'll see in a little bit. Okay, the consequence of measurement error is typically a bias that leads to a reduction in magnitude, or a bias towards zero. It shouldn't change the direction of the true estimate. And so if the true estimated effect of the treatment is, say, -5, it's going to bring you towards 0, so maybe -2 you'll get as a result. You shouldn't get some positive number. Okay, so what can be done about measurement error? Well, typically there's nothing that can be done. Okay, there are some fancy techniques out there, but they're very unstable, and I put very little faith in them. And so most of the time it's just something you have to live with. Okay, let me give some insight into determining the direction of the bias. And so let's say that we want to estimate the effect of a college degree on income. Now, obviously, there's going to be many biases associated with this, some covered in the prior videos. Okay, but let's say that this is the true distribution and the true means among those who really have a college degree and those who really do not have a college degree. Okay, so it's a $20,000 difference in income. Okay, but what would happen if, say, a random sample of the no college degree people got classified as having a college degree? Okay, well, if it's a random sample, we wouldn't expect this 60,000 to change much. Yeah, it might increase or decrease a little bit, but depending on how many people are in the sample. But we wouldn't expect this to change. But now we're adding all these people with an expected income of 60,000 to this group right here. And that's going to bring the average income down for this group. Likewise, if some of these people with a college degree got misclassified over in the no college degree category, well then that average income is going to go up. And so while 20,000 might be the true difference, after there's some measurement error, then the difference is going to be much smaller than that. Okay, now the difference really shouldn't change signs unless there's perhaps more people who are incorrectly classified than correctly classified. Then it may actually change signs, and it looks like those with a college degree get less income than those without a college degree, but that's unlikely. So it should be a downward bias towards 0 in the estimated effect of college, but it's not necessarily a downward bias with measurement error if it's not random who switches from a given category, or even if more variables are included in the model, then it's possible you might not get that downward bias. Okay, so it could be that the people among the no college degree category who do lie and say they have a college degree, well, those might be people who have really high income and maybe they're embarrassed that they don't have a college degree for some reason. Okay, and so that means that this would actually go up higher, this would come down lower, and so then with the measurement error, we'd get a larger increase, okay, or bias upwards in magnitude. Okay, but the most likely situation, especially if it's a random selection of those who get misclassified, is that there'll be a bias towards 0, towards minimizing any difference. Okay, so let's demonstrate the effects of measurement error using the National Longitudinal Survey. And so I have a sample of males from 2004. They're roughly in their 30s and 40s at this time. And so a very quick, simple model. This is using years of schooling rather than college education. And so a simple model has the coefficient on education being 8264, saying on average each year of schooling is associated with $8,264 more income. Okay, now obviously, as I said, that's going to be subject to many different biases. If I were to control for the AFQT score, that's the Armed Forces Qualification Test score, which was given to about 94% or so of the respondents in the NLSY, and it's basically a measure of aptitude. So if I include that, then the estimate goes down from 8264 to 5484. Okay, and so what's likelier to be closer to the true effect? And I'm going to guess this one right here, the 5484. We're probably still way off, but at least we've controlled for, or at least adjusted for, a measure of aptitude. And so I think we're actually doing a little bit better with this model. Okay, so now let's add some measurement error to the key X variable. The key X variable would be years of schooling or education. And so what I did is I added 1 year of schooling for a random sample of about 10%. I subtracted 1 year of schooling for about a random sample of 10%. And look what happened to the coefficient estimate. It went from 5484 down to 4317. Okay, and that's typically what happens. When it's random as to who gets misclassified, then it's going to be biased towards 0. Okay, and what's also interesting here is that the AFQT score is now getting credit for some of the years of schooling effect because we're not measuring years of schooling very well. That estimate is coming down here. This one is going up, probably because these two variables are positively related. Okay, now let's add measurement error to the control variable of the AFQT score. So again, for about 10% of the sample, I added 5%, and for another randomly selected 10% of the sample, I subtracted 5 points from the AFQT score. AFQT score is measured on a 0 to 99 scale. And so here I'm just bringing down equation 2 here, where I included years of schooling and AFQT score. Okay, and then when I add that measurement error to the AFQT score, then the estimate goes down to 247 for AFQT. The coefficient then goes slightly up for years of schooling. Okay, so that added measurement error to the control variable. And so then the question to ask is, should we exclude the AFQT because we have measurement error? And so basically what this asks is, well, is this a better model right here? And by the way, these question marks, I forgot to write it down when I did that randomization, but don't worry about that. Okay, so the question is this the better model right here, or because there's measurement error in the AFQT score, we should drop AFQT and go back to equation number 1 where we don't have AFQT? And what I would say is that we still use it, even though it has measurement error. There's still a lot of good explanatory power in the AFQT score, and it's helping to some extent to reduce omitted variables bias. And so I would say that this is the better model, despite the measurement error, which is biasing the contribution of the AFQT score. Okay, now let's think about what certain results tell us, and we'll use the basketball hot hand as an example. And so this will be a typical model to estimate whether there's a hot hand. And so you have some 0-1 variable for whether a basketball player makes a given shot. Hopefully it's something like a 3-point shots, perhaps even the 3-point contest where there's a standard shot. Okay, and so they'll regress that on some variable that tries to indicate, well, how well are they playing? Might they be in the hot hand state? And so what's been used has been an indicator for, did they make their prior 3 shots or not? Okay, then perhaps other variables are controlled for. Okay, so let's say that this is true basketball shooting percentage under the normal state, where a person would hit shots at a rate of 50%, and then the hot hand state would have people hitting shots at a 70% rate. So it's basically a 20 percentage point hot hand effect, 70% minus 50%. Okay, so the problem is that whether you made your prior 3 shots or not is not a good indicator for whether you're in that hot hand state. Okay, you may have made only 2 of your prior 3 shots, but still be in the hot hand state. So you're really in the hot hand state, but you get classified here in the normal state. Okay, and that means that this percentage is going to go up. Okay, likewise, you might be in the normal state, and yet out of luck, you made your last 3 shots, and so you get misclassified into the hot hand state. Yes, that happens. And that's going to bring this percentage point down. And so the difference in what we see in the data is going to be something much less than 20 percentage points because we're not accurately assigning people to the normal state and the hot hand state. Okay, and so back a couple slides. If you remember, this is that key X variable not representing well the concept you're trying to capture. Okay, so if we get an estimated beta 1 here of 0, what can we conclude? Okay, well, it's possible that it means there's no hot hand effect, but it's also possible that just the measurement error is driving this estimate towards 0, that we're really misclassifying many people. Okay, well, I did something like this in a past study, and I found a coefficient estimate of around 0.03, which was significant, meaning a 3 percentage point increase in the probability of hitting a shot if you're in the hot hand state as I defined it. And what that probably tells us is that, well, there's still going to be some measurement error, and so what I would say is that the hot hand effect is probably much greater than 3 percentage points. Okay, because I'm almost certainly misclassifying people, and that's going to drive the estimate towards 0. So this 0.03 is probably indicative of something much larger. Ignore my spelling mistake there, which I just noticed. Okay, a couple details. So measurement error, again, as we point out, it's not a reason for excluding a control variable. If there's measurement error in the dependent variable, it's rarely a problem. What it will do is probably create a higher standard error in your various coefficient estimates, but it shouldn't cause a bias to the coefficient estimates. Okay, so what you want to look for to detect problems is, could there be non-trivial error in the key X variable? And could the key X variable poorly represent the concept you're trying to measure? And that's what we saw in the last example with the hot hand, that making the last 3 shots is a poor indicator for whether the person's in the hot hand state or the normal state. Okay, next video will be on big questions 5 and 6 on whether there are mediating factors or outcomes as explanatory variables or control variables.